This is test 3 review. So let's look at problem 1. The sample is selected from a population with a mean of 50. After treatment is administered, the mean is 55, the variance is 70. This sample has 5 scores. You're going to calculate the estimated standard error and then determine whether the sample is sufficiently greater to conclude that the treatment has a greater significant effect. Use a one-tailed test with alpha 0.01. So step 1, you're going to do the hypothesis. And in a one-tailed test, you're going to use greater than or less than. So in this case, the researcher thinks that the treatment is going to have a greater significant effect. So your H1, which is what the researcher thinks, would be mean is greater than 50. The opposite is your null hypothesis of mean is less than or equal to 50. So you're going to draw your picture. You're going to put the tail on the right side, which is the greater than side. You're going to find the degrees of freedom, which in this case would be 4 because n is 5. And you're going to find your critical value using the numbers that you're given. So if you're given degrees of freedom 4, alpha 0.01, go to your table and you'll find a critical value of 3.747. Then you can find the estimated standard error. You're given s squared, you're given n, so you can find an estimated standard error of 3.74. You can put this information into t, and you can find t is equal to 1.34. Put an x on the graph. And you're going to fail to reject the null. You're not in the tail. You're not in the rejection region. Instead, you're in with the other 99% of the people. So here's how you would write your sentence. The treatment does not produce a greater significant effect. T of 4 is equal to 1.34. The probability of obtaining it is greater than 0.01, and you have a one-tail test. All right, let's look at the next problem. So we have an independent measures study looking at how the brain chemical serotonin is related to aggression. So you have the sample of rats that's the control group. They receive a placebo, meaning it's really nothing, doesn't affect anything at all. The second sample receives a drug that lowers brain levels of serotonin. And then they test the animals by recording the number of aggressive responses. So the question A is, does the drug have a significant effect on aggression? Use the alpha level of 0.05 two-tail to determine. Part B is to compute Cohen's d to measure the size of the treatment effect. And here's the data that you're given. Okay, so step 1, you're going to find the hypothesis. Well, in an independent studies, this is comparing one group to another group. You would just say the null hypothesis is the mean of group 1 equals mean of group 2. And then the research hypothesis says the mean of group 1 is not equal to the mean of group 2. Then you're going to find your pooled variance, which is just SS1 plus SS2 over DF1 plus DF2. So these are easy to find because you're given N and you're given SS for each one. So I found a pooled variance of 6.29. You should also go ahead and draw your picture. This is a two-tail test. The pooled degrees of freedom would be 43 because the degrees of freedom for the first sample would be 19 and the degrees of freedom for the second sample would be 24. Add them up and get 43. That's your pooled degrees of freedom. You're going to use alpha 0.05, two-tail, look in your chart, and you should find critical values of positive and negative 2.021. Remember, the chart only gives you positive. Your picture is what tells you if it's positive or negative. Now you're going to find the estimated standard error. So you're going to use the equation square root of the pooled variance over N1 plus the pooled variance over N2. You're not going to square anything on the top. SP squared is the symbol for pooled variance. So your pooled variance was 6.29. You simply put 6.29 in the place of SP squared in this equation for each spot. So you have 6.29 over 20 plus 6.29 over 25. So you end up getting 0.75. Now you have everything you need to solve for t. So M2 minus M1 over the estimated standard error gives you a negative 5.33. Okay, place your x on the graph, and you're in the critical region, so you reject the null. Next, you're going to solve Cohen's d, and remember Cohen's d is always positive, so another way of making sure that it's positive is to just put absolute value signs around the equation. Or you can just make it positive at the end when you're done. Either way works fine. Here I'm showing absolute value signs. So again, when you're using d is equal to m2 minus m1 over the square root of the pooled variance. Remember, SP squared is the symbol for pooled variance. You don't square anything. You just take the pooled variance of 6.29 and put it under the square root sign. You solve and you get 1.59. So here's the sentence that you should write. Low serotonin levels cause an increase in aggression. T of 43 equals negative 5.33. The probability is less than 0.05, and D is equal to 1.59. All right, let's look at this problem where we're trying to determine if relaxation training will affect the number of headaches. So you have 8 participants, and they're going to record the number of headaches they suffer, and then they're going to receive relaxation training for a week, and then they're going to record the number of headaches again. So we're going to compute the mean and variance, and then we're going to determine if the results indicate a significant difference. We're going to use a two-tail test with alpha equal 0.05, and we're going to compute Cohen's D and R squared. So the data you're given is before and after scores. So the first step you're going to do is you're going to do a D column and a D squared column. So the difference, I typically just do D2 minus D1, or X2 minus X1, which would be 14 minus 16. That would give me negative 2. 11 minus 15 would give me negative 4. So forth and so on until I have the difference values. And then I add that column up. So the summation of the D would be equal to negative 16. Then for the next column, I do a D squared column, and I just square the D column. So negative 2 times negative 2 would be 4, and so forth. Square all of your values, and then add them up. So you should get summation of D squared is equal to 46. Now let's look at what your hypothesis would be. Basically, the mean of the different scores is going to equal 0, meaning there's no difference. You're in there with everybody else. Or the research hypothesis says the mean of the different scores is not equal to 0, meaning you're different. So let's look at the picture we would draw. First off, we would determine degrees of freedom. In this case, there are 8 participants, 8 people that have before and after scores, so the degrees of freedom would equal 7. Alpha is 0.05, two-tail. So you draw your two tails, you look in the table, and you should find critical values of plus and minus 2.365. Next, you're going to find the mean of the different scores. Well, that would just be equal to summation of D over N. Summation of D you found is negative 16, and N is 8. There are 8 sets of scores. So the mean of the different scores is equal to negative 2. You're going to have to find your sum of squares in order to complete this problem. Well, you know the equation for sum of squares. It's summation of D squared minus summation of D squared over N. Fill in the numbers that you know. And that number in parentheses, the top should be negative 16 squared, not negative 1.6. And you would get an answer of 14. S squared would be equal to SS over degrees of freedom. So the sum of squares you just found was 14. And degrees of freedom you found earlier is 7, so your variance would be 2. Now you can find the estimated standard error of the mean difference scores, which is the square root of the variance over N, and you would get 0.5. Now you have everything you need to solve for T. So T is the mean of the difference scores over the estimated standard error of the mean of the difference scores. So it would be negative 2 over 0.5, which would give you negative 4. Put it X on your graph where negative 4 would be. Notice it's in the rejection region, so you reject H sub O. You reject the null. Now let's find Cohen's D. Again, I'm using the absolute value just because you always make Cohen's D positive. So if you plug in your numbers for the mean of the difference scores, which was negative 2, and S, for S you have to take the square root of S squared. Well, S squared you found as 2, so S would be the square root of that 2. So you get 1.414 for S, which is the standard deviation. So you would get D equal to 1.414. Finally, you're going to find R squared. So remember, this T that you put into R squared is the T that you calculated. In this case, it's a negative 4. So if you square the negative 4, you'd end up with 16. So 16 over 16 plus 7, you'd end up with 0.70 for percent variance. So your equation would be written like this, your sentence. Relaxation training has a significant effect on the number of headaches. T of 7 is equal to -4. Probability is less than 0.05, and D is equal to 1.41. You would also say, comma, R squared equals 0.70. All right, here's another problem. Using the data below, which are just X and Y data sets, find a Pearson correlation, graph the data, show a line of best fit. Okay, well, I just graphed it. I just threw the numbers into SPSS. So remember, when you graph it, you treat it like points. So you have an x4 and y is 3. That's like a coordinate point, 4, 3. So you go over 4, up 3, and put a dot. And then the next point would be 4 and 7. So you'd go over 4, up 7, you'd put a dot. So you're going to plot all 8 of these points that are given to you for the x and y column. All right, now to find a Pearson correlation, you're going to have the summation of the x column, which I got 24, the summation of the y column, which I got 48, and then you're going to have to make an x squared column and a y squared column and an xy column. For x squared column, remember you just square all the x values and then add them up to find summation of x squared, and I got 88. For y squared column, you're going to square all the numbers in the y column, then add them up. I got summation of y squared equal 312. And then for xy, you're just going to simply multiply the x value times the y value. So for example, in the first one, it would be 4 times 3, you'd get 12. The second would be 4 times 7, you'd get 28. You're going to add up the xy column. The summation would be 139. So you need those 5 summations at the bottom of this table to compute a Pearson correlation. So first off, just know that there are 8 numbers in each column, so n is equal to 8. And then you're going to substitute all the sums that you found that are at the bottom of the table into the sum of squares equations and the sum of products equations. So let's do the x one first. So sum of squares for x, substitute in the numbers for x, and you would get 16. Now find the sum of squares for y, plug in the numbers for the y columns, and you should get 24. Finally, you're going to do the sum of products. Plug in all these numbers, and you would get -5. So your last thing that you would need to do is to find R, which is the Pearson correlation. So basically, it's the sum of products, which is -5, over the square root of the sum of squares for x, which is 16, times the sum of squares for y, which is 24. So you solve this, and you should get R is equal to -0.26. So negative correlation means that your line of best fit is falling. So is it falling? Is it like falling down a hill? Yes, that's what your graph looks like, so that fits pretty good. 0.26 means, oh, that line's not really great and it's not very close to all those points. It's not a very good correlation. And if you look at the graph, you can see the points are kind of pretty far apart from that line. So that makes sense. All right, so we're going to take the same set of data and we're going to find a Spearman correlation. So if you graphed it and showed the line of best fit, it'd be the exact same graph as you had before. So basically, a Spearman is even easier. You just have to rank the data. So you're going to rank the X column. So there's going to be rankings from 1 to 8. And some of them you might have to average the rankings. And then you're going to rank the Y column. And then you're going to find the difference between the X column and the Y column. Okay. In this case, to find D, I just said the bigger number minus the smaller number. So I said X rank minus Y rank, and I got 5. And then I squared it and got 25. The same thing for the second set of scores. The X rank was 6, the Y rank was 5.5. The difference of those is 0.5. Since I'm squaring them, and all I care about is a D squared for Spearman, it doesn't matter which way I find the D column. I can do the second one minus the first one minus the second. Makes no difference at all, because all I care about is that final D squared column and that summation, which gives me 98. So that's the only number I need, that 98, to put into the Spearman equation. So the Spearman at R sub S is equal to 1 minus 6 times summation of D squared. Well, the summation of D squared I found in my table was 98. And I know N is 8. There are 8 sets of points. So I plug in 8 for N, and for summation of D squared, I plug in 98. I solve my equation, And remember, you're going to do 1 minus at the very end. That's the last step you're going to do. So you're going to solve the fraction part first to get 1.17, then subtract it from 1 on the last step, and you get a Spearman correlation of minus 0.17. Again, it's negative, indicating the line is falling, and you know that's correct.